Hi everyone, I will be presenting from Zero to VS Code, a framework approach to language support. So before we start, I just want to present our team. My name is Alexandre Lachance. I'm a master's student at McMaster University. We're all working under Dr. Sébastien Masser. We have Noel, who is a research assistant, who's helping us at McMaster University too. And over the summer, we had Maël, who was an intern from Université de Montréal. So let's start with the problem we're trying to solve. So as part of our research, we talked with a lot of P4 developers and identified some problems with their workflow. P4 is a domain-specific language to program switches, routers, and other network devices. And the developers that use that language have little to no tooling available when writing their code. And so most of them are writing in like Vim, just like if it was a plain text file. This makes like development using the language harder, longer, and more prone to mistakes. So we looked at the current solutions to provide editor support for DSLs. We looked at MPS, Xtext, Metacase, and others. But the problem with these solutions, it only provide end-to-end solutions. So using them, you define the DSL, it builds for you the compiler, the editor support, and everything. What makes our use case different, though, is that the language already exists, the compilers already exist, so we don't want to rebuild the entire language. So we will be considering those as black boxes and only working independently from them. So for our solution, we turn to language servers. And for those who don't know, language server or the language server protocol is a way to standardize communication between an editor like VS Code and language-specific features. It was developed by Microsoft and can be for VS Code, but it is implemented in a lot of different editors. Like, well, in this image, there's Atom, which is dead, but there's a lot of other editors. IntelliJ just added language server support, or Vim and Sublime also implemented. The language server provides stuff like completion, diagnostics, highlighting. So our goal was to write a language server for P4. So easy enough, right? Just write the language server. Well, turns out writing a language server is hard. P4 itself alone has multiple open source language servers, but none of them are maintained anymore, and none of them are close to being complete. For example, there was the P4 analyzer worked by Intel, which is now dead. There's also the P4 LS that was worked on a couple years ago, but is not maintained anymore. Well, why is it hard? Well, you start by writing feature by feature, hacking stuff together, but soon you realize you're basically writing an entire compiler front end, and the complexity kind of explodes from then. For example, if we take code completion on a monolithic architecture, the IDE sends a code completion request using like standard protocol data structures, and the LSP returns a completion list. Well, to return that completion list, the language server needed to look up the context of where the completion was requested from. It needed to look up the context of the completion. So if you're calling a function and you want completion for parameters, it's not going to be the same completion that when you're declaring a class, for example. And then it needs also to build the response corresponding to the language server protocol. And when you're writing all that, you're entangling the language, here in this case it's P4, within the logic, and it gets very hard to keep track of all the different features. So we then looked at the language server as an assembly of different services. Some are technical, like the gateway that interfaces between the editor and the language server. Others are data related, like the AST or the symbol table. And there are some that are business, so the logic to get the completion list or filter that list. So we are implementing the P4 language server as an assembly of such different components. But then we looked at these different components and we thought, yeah, well, those are not like tied to P4. So if there's a way to like extract the language, but rely on these same abstractions, on these same services for other languages, that would make a great framework. So yeah, we factorized the redundant mechanisms into language agnostic abstractions, and we designed the code to only rely on these abstractions. For example, at the bottom here, we have the entire code for the language server that you need to write to declare language server, and you need to provide a rules file. That rules file defined how the syntax tree is parsed to generate an AST and a symbol table. I'll explain further in the demo, but yeah. For the demo, we're not going to be using P4, so it's a networking language and it can be quite complex to understand. We're going to be using the JPipe DSL instead. JPipe is a language that's kind of similar to Plan2ML, for those who are familiar with that. It's developed by other members of our research team, and it's used to basically generate justification diagrams using different building blocks. In this case, like evidences, strategies, and conclusions. So let's get to our demo. Stop sharing that. And this one. Here. And we see the screen. I don't.
Yeah.
I don't.
Lots of terminals at the moment.
Yeah, I'm seeing 3 terminals.
Perfect. So here. So to start, we built a cookie cutter to generate the basic structure of the project. Cookie cutter is just a templating tool for projects. So we're gonna grab the template at acedesign/lever framework cutter and re-download it. It's going to ask us a couple questions. So, for example, our language here is JPipe. Language is going to be JPipe2. The file extension is JD for JPipe files. We're going to say that the author is acedesign, publisher is also acedesign. And this is going to generate us a project here. This project contains a language server, contains TreeSitter and VS Code. TreeSitter, for those who don't know, is a parsing library for defining the language grammar. I won't bore you with writing the grammar, so I'm just going to copy and paste the grammar, but it's basically translated directly from the Antler grammar of the language. In this case, it's a pretty simple language with only like 61 lines in the grammar. But yeah, so we're gonna generate our grammar using TreeSitter again. So TreeSitter, all right, that's gonna generate your grammar, and we're gonna just test to ensure that the grammar is working. We're gonna grab a couple examples of the language. We're gonna parse. We're gonna parse our file with TreeSitter. So TreeSitter just provides us with a concrete syntax tree of our file. I'll just open up the file so we have a reference of is example simple. So for example, here we have just a source file, the justification body evidence. So justification body evidence. So after you've defined your grammar, and then work on the language server itself. So the language server generates us a project file that imports our TreeSitter grammar. and it also imports our framework and another library that's used to do async stuff. Generates you the main code, which you don't really need to change for now. That imports the rules file and starts the server with the rules and the tree-sitter language grammar. More interesting stuff is here in the grammar. So I'll just do an overview of this file. First, you start by defining the language, the name of the language, and the file extensions. You could add more if you wanted. Here we just have JT. Then you define the keywords that are present in your language. After that, you have the symbol types. So all the different symbols, for example, constants, variables, functions, you all define those here with the completion type, which doesn't really matter. It's like the icon that it shows you when it provides you the completion in the editor, and the highlight type that can change the color of how it's going to be highlighted in your editor. Then you have the global ST rules. That are basically rules that are present in the entire file. So for example, comments can be anywhere in your file, in your code. So you would be defining those kinds of rules here. We're going to ignore that for today for simplicity's sake. And then you have your AST rules that are used to parse the tree-sitter CST into an AST and a symbol table. We'll just start by defining the keywords here. Again, I'll just copy and paste them. And sorry, I'll just copy and paste them again. So yeah, why is it not already? Copy and paste. Okay, there you go. So those are all the keywords of that are present in the language. We'll just compile that just to make sure everything's working. And then we're gonna just go make the VS Code extension. Okay, that was an error. Great. Okay. Why is there an error? Great. Okay, I copied pasted that too. Compile. And there we go. So now we'll jump back and we'll jump into our VS Code extension. You don't really need to change the code for the VS Code extension. We'll just install all the dependencies. Should be very quick too. Then we'll package the extension and install it, just so we can look at the keywords and a couple other things in VS Code. There you go. And then we'll just package the extension using the Microsoft stuff. It's going to make us our VS Code extension, and to install a VS Code extension is just this command, so code-install extension, and so we'll jump into VS Code and just reload the window, and there we go. Install the VS Code extension. Here we get the highlighting for the keywords we provided, and it's smart highlighting. So if we do like this, and differentiate, since it's based on the language grammar, it can differentiate that that's not a keyword in this case. So we'll go back to our grammar, to our rules file, and we're gonna continue on that. So first, we wanna create a symbol for SU1 to get completion and syntax highlighting for for symbols. So we'll start with the evidence. And then we can also use the tree as a reference. So the evidence is in a justification, which is in a justification body, and then you have your evidence. So we're starting at the root. We want to query. We want to start by defining the justification AST node. So we want to query in the tree setter tree. We want to query the justification. And with that, we want to generate we want to parse our rule that's going to be called justification. Find the justification rule, name, justification, and that justification is going to have children that are going to be, in this case, it only has its body as a children of this use case. So we're just going to query body. Again, I'm using justif body here in the tree setter tree. So I'm querying that, and then I'm generating another rule that's going to be used. So justification body, and then we just need to define the justification body. I'll copy paste. Sorry, I'll just copy paste that. The justification body rule that has evidence as a job. So pretty repetitive here somewhere. So we'll define the evidence. So we're just like generating how to parse the tree setter tree into an AST. And children. So now it gets a bit more interesting. So for the evidence, you can see that it has a child, which is identified element that has an ID and a name. In this language, the ID here is the symbol name we want, and the name is a string. So we're going to define two children. So the ID. But since it's nested in identified element, and we don't really want that's more for parsing. We don't really want identified element node in our AST. We can provide a path instead to get nested components in our CST. So we want to go to our identified element, and then we want to either get the child that has a field name of ID or a kind ID. Just to make it different, I'll get the field name ID. And then we're gonna generate another, we could just make a rule and say ID and then define the ID, or instead we can just say direct if we don't want to write an empty rule that just has a name. So direct ID is the equivalent of saying a rule, no name. ID is just a shortcut. So yeah, so we have the first child, which is going to be ID, and then we're going to make a second child, identified element, and here we want to get the name. We'll say name. Send the letter just to make it sense. Now we've defined how to parse our RST, but we've not defined how to generate our symbol table. To specify that here we're creating a symbol with the name ID, we just need to add the field symbol and say it initializes a symbol of type evidence, which how do you find the name of the symbol? Well, you get the node name. In this case, it's ID. We also need to define the symbol type evidence. So we'll just remove variable and say evidence. We can keep those as the same, as it doesn't really matter. So we'll compile all that. Folder, I think. Yeah. Sure. We get an error again, great. So more rules, and we find where we made an error. Oh, we forgot the comma here. We get another error, and it's missing a field. That's weird. And it should be complete. Type evidence, no name. If it doesn't work, I'll just copy paste the working solution, but should be missing no name node. I said no. I said name no name. Miss name node. Okay. And we'll combine that. So we can go back to our VS Code and reload the window. And if everything's working well, yeah, we get highlighting for our symbol here that is an evidence. You'll notice though that we're not getting highlighting here for the same symbol, since we've not defined that here we should be looking for a symbol usage. So that's the next step we're going to do. But you can see already that we're getting completion for the symbols that are defined in here. We'll go back and we'll define the supports here so we can get the usages. I won't bore you with writing those rules too, so I'll just copy paste those rules. Hopefully, yeah. So here we're defining relation, which is where supports is being used from one ID usage to another ID usage. And just to say that the framework should look for a symbol usage here, we annotate it with symbol usage. We'll just need to add that to our justification body, so it can query it. Not our justification body. What can I say? Relation. So in our relation is here. It's in a justification body. So it's that, and we cargo run. We get an error again. Great, we forgot a comma again. Where did I forget a comma? Probably here. Yep. And we can reload this window. And here you'll see that we get highlighting here for the symbols where they're being used. And we also get, by default, we get go to definition. So I can jump to the definition of a symbol. We can also rename a symbol. It's going to rename all of the usages, and it's not going to, if I do SU3 here, for example, just simple find and replace. So if I do this, it's not going to replace here. So that's the basic of it. One problem here we'll notice, if we open a file, it's a bit more complex. We have no notion of scopes yet. So if we like rename this to something, it's going to affect, well, in this case, it just didn't rename anything else because we have like no notion of scopes. So it's kind of open. So if we go back to here, we'll just have to specify where the scopes are. In our language here, the scopes are defined by the justification. So the one justification knows one scope. And we also have like the root scope. The root scope is already defined. So at the root, we say that that is a scope. We'll also just say that justification is also a scope. And if we rerun that, and we reload, we should get proper scoping support if everything worked well. There you go. So if I rename SU2 here, it renames correctly and there's no issues. It didn't rename SU2 here either. Yeah, so I'll just complete the, I won't write all the rules for this. I'll just copy paste the rest of the rules into our file here, just so you can see like the end result of an entire language here. If we have a small language, the rules file is only 881 lines. It's not really the full language yet, but close enough. No, we should see pretty colors. And yeah, so we get highlighting for everything and we get completion for everything. So SC1, for example, ST1, we get here. Oh yeah, something I forgot to mention for like syntax highlighting. For example, is the string here. The name, you can, for a child, you can specify the highlighting type and just say it's a string. So I think that's pretty much it for the demo. So if you have any questions, you can go ahead, I guess.